All right, so did y'all come to my talk yesterday?
Yeah, I was on Zoom.
Okay, you're on Zoom, did you?
I wasn't aware of one.
Okay, all right, that's fine. It was not a prerequisite, you didn't have to do it, but I did show off some of the parts of the code, talked about some parts of the code. This is my first time trying to show somebody outside my research group this. This is actually, I just started a sabbatical, sabbatical leave. And actually one of my goals for a sabbatical is to share and teach my codes for other people. So you're my sort of guinea pigs for this. And what I'm going to do is, in addition to the survey, I'm going to have like cards here. And if I sometimes think the tactile thing of writing stuff down can be really useful. So if there's like things that you like, features that you want to have or questions you have, you can either submit them online or write them down on a card, and that way I can get some feedback on what worked with it. So I have no idea how this is going to go, honestly. Okay. Since there's only 3 of y'all, this should be hopefully get ourselves sort of oriented quickly. Who here has Python experience? Okay, all right, good. That's usually a given these days, but I'm gonna take it for granted. All right, who here has GitHub experience? Yeah, so, okay, kind of sort of like you've heard of it, you know how to do. Okay, so how many of y'all have used like command line, git clone, git pull, git push, commit? Okay, you're a little shakier on that. Okay, that's fine. There's a handful of things we'll need to do to kind of get started. So the way this is going to work is one of the things we've been doing with Swiftest is trying to put together a set of documentation pages. And rather than reinvent the wheel for this workshop, I basically just adapted some of our documentation pages verbatim to some exercises. So like the first 2 things I want to start with, there's if you all gotten this link at least. All right, so if we're all in here, the first 2 sort of things we're going to do, the basic simulation, the detailed simulation. These, I actually created some Jupyter notebooks that more or less represent what's in these user guides. So I'll just kind of show you the user guide. Actually, let me start with the Swiftest documentation page, because the wonderful thing about having really good documentation is that I get to refer to it. So I use this myself quite a bit, so it's been a really useful thing, but it's by no means comprehensive and finished. So part of my goal is to figure out what's needed. Okay, so let's start. First thing you want to do is you want to clone this repository, because this repository is going to have the files you're going to need to kind of get started with things. Okay, so to clone something to your local machine, what I usually do is, you could basically select the HTTP since you're not a member of my group. I'm going to do this one. Hit a little button there. Then you're going to, I touched my touchpad. Okay, so, okay, for who here is sort of comfortable with like file structures, and what kind of machines are we on? Are we on Linux or Mac? Mac. Yeah. Good. All right. Thank goodness. Right. Somebody had Windows, I'd be like, no. I taught a class once and like half the students had Windows PCs, and a lot of the scientific codes don't work in Windows because they're like, we live in Linux world. Mac at least is a POSIX operating system, so it's compatible, and I use Mac for everything. All right, good. We all use the terminal program much? Okay, good. I'm in the right place. Okay, so first order of business, you want to like find a place for your repository. I have my own scheme for storing these sort of things. So I've already actually set up my system. I'm just going to go into it.
Would it be too sleepy for you guys if I try to ask the lights here? No, it's the other way. That's too much.
Yeah, that's okay. Yeah, that's okay. We got our right screen.
Just because the other one's going to be hard for me to.
Yeah.
Yeah. You know what I can do is I can make the screen bigger.
Yeah.
There we go.
You always have to share a chunky terminal when
Yeah.
not just
We'll get to VS Code and we'll see how that works.
Yeah.
Okay, so I've already cloned this, but basically the command you do is git clone and then the URL that you copied from there. So you do that, and once that's done, it'll clone the repository, and then you can CD into it. So I'm actually running 2 workshops, so I got a creator maker one tomorrow. Okay, so you should then have the repository set up with the files in there. You're not going to see the VNV or this notebook, but you should see everything else here. So we all got that? Okay, so next order of business is we want to create an environment to and if you've done this before, like I actually just updated some of the repository like half an hour ago. So if you previously cloned it, just do git pull, make sure you're up to date. Okay. Next thing is I'm going to be using Jupyter Notebook, actually Jupyter Lab, to kind of show how things work. Just because I typically don't use Jupyter very much. I actually don't. I try to avoid it because as soon as projects get complicated, Jupyter becomes really cumbersome and it doesn't play well with GitHub. There's all these extra things I had to do to get these notebooks up there without like causing a bunch of issues. So, but it's really useful to kind of show off capabilities and have like this real time kind of run a command, see what happens kind of thing. So I really like it for this kind of environment, but I typically don't use it. And once we get away from the basic stuff, I'm going to move strictly to Python scripts and command line stuff. Right? But for now, we want to get Jupyter Notebook. As somebody who runs a lab with a lot of students running our codes, which are all works in progress, and I feel like that I spend an enormous amount of my time troubleshooting people's Python environments, particularly Conda. So my experience has been that once I found like a system that works, it's like I do that and I don't touch it. I kind of stopped using Conda just because it's just a pain. So I typically now use virtual environments that are kind of attached to a project or a task or something, right? Okay, so if you here, use virtual environments to set up the Python environment for kind of, sort of. All right, okay. Well, on my machine, which is a Mac OS, I've already got Python 3.13 installed. So the Swiftest, I think, works back to 3.10. Does not work for 3.14. I found that last week when I was preparing for this. Some of the dependencies haven't upgraded yet. I think it just came out. So just to be safe, I'm using 3.13, but it should work on 12 or 11, so whichever one you have. On my Mac, when you install the official Python thing, this is how you access the particular version. You run the VNV module. That's what -m means. So I'm going to -m VNV to run the VNV module, and I'm going to create a folder called VNV that contains that virtual environment. So that's what these commands mean. So starting with Python 3.13, use the VNV module, create a folder that contains my VNV, and I'm going to call it VNV. So they're actually these VNVs are 2 different things. They're saying 2 different things. Okay. All right. We all got that part?
Yep.
Okay. So what I'm going to do, because there's only 3 of us here, so, and I've taught these sort of things in classes, so I know that like, if any of you get behind even by a step, like that compounds. So if you need me to stop and slow down, I need you to like interrupt me and stop me so that I can get you on the same page. Because otherwise, if you get like 5 steps behind, like we're gonna have to all stop anyway and catch up. Might as well get that beginning. Okay, so next is you need to activate your environment. And since I've already created the environment, but I haven't activated yet. Actually, you know what? I like to demonstrate that it's so easy to do that I can just start from scratch. You don't have to love your environments. You can delete them and start them again. So I'm just gonna run these commands in real time. Okay, and then now I'm going to activate the environment. Okay. Swiftest there's a release. That means that I have compiled. It is a Fortran code mostly with the Python front end. And I spent a lot of time actually gating the Fortran side to be sort of invisible to the user. So there are pre-compiled libraries. They're compatible with most people's machines, should be compatible with everybody's machine in here. The only one that doesn't really work in is Windows. It worked a little bit a few versions ago and then stopped. I don't know why, and I haven't spent the time to figure it out. So you should be able to just do pip install Swiftest. We're actually going to install Jupyter Lab 2, since it's not a requirement of the package. Okay. Since I started with a fresh VNV, it's going to download and install these things. So you should be seeing something similar to this, similar-ish. Okay. You got some issues?
I need 2 minutes.
Okay.
I'm having an issue with my
It
Python.
doesn't have 3.13.
Oh, you can use 3.12, 3.11.
I tried, yeah, because I think it's the update come out.
Oh, no, it's fine. You just need to, it always gives this when, if you've got an out-of-date pip.
Right.
So you can just, what I would do is I would activate your environment. So I think it's created just fine.
She didn't create the environment yet because she tried to do it with 3.13.
Oh,
But you could just do, if you just do Python 3, yeah, that'll be fine. And that'll just make your own virtual environment and it'll be Python 3.12.
Oh, what happened? Why is it?
It's gone.
Okay.
So I did make the VM.
You're not using C shell.
Oh, no, I'm using my 10.
Okay. All right, now try the pip install
Yeah.
Swiftest Jupyter Lab.
I am having Swiftest install issues.
Okay, let's see. Oh, you've got, let's see, do you have an Intel machine?
I might, yeah.
It's an old PC, old computer?
It wasn't that old when I got it.
Yeah.
Yeah, 2020. Should be Intel i9. I don't think it's on the M1. It was just.
Yeah. It no longer works there. Do you have a Linux virtual machine you can use? The Macs are no longer supported, so I can't get the build system to work on Intel Macs anymore.
Okay.
They're all sort of not, all been deprecated off of the GitHub stuff. Okay, so have you have access to
Yeah,
quickly a Linux?
I have access to your own machine.
Yeah,
Okay, once you get on that, because that's fine. I do a lot of things remotely anyway.
Yeah,
And it's basically identical experience on Linux as it is on Mac, so.
that's fine. Yeah.
I think mine's set. I tried
So I did it for the condo, but I'm.
Oh, are you in Conda? You've already got a Conda environment?
Not in it right now, I'm just in my.
You might just have, let's see.
Kill this. I'm ready to.
Oh, 2.7. Oh my, okay. Okay, so let's get you, first of all, I want to see make sure you're not gonna have the same problem as. Sorry, I'm trying to get to this.
Sorry, I have a hot button over
Yeah.
there.
No worries.
Okay,
Okay, I'm
I'm
good.
quick.
Okay, let's just go to the official Python site and get Python 3.13. They're gonna want you to download Python 3.14. We're gonna ignore that.
I did it on my computer,
Good.
Yeah, that's good.
everything else is updated.
Yeah.
Well, I'm guessing, okay, so the problem with Python, they try to make it convenient by letting you have like every version of Python at your fingertips, but that also means everything's complicated because you don't necessarily know which version of Python you're actually using. So there is probably a shell environment variable set to look for that version of Python. I'm guessing you had some old code that was only compatible with Python 2 that you needed. So what we're going to do is we're just going to download the Python 3.13. We're going to install that.
See if it works.
Now you see why I'd be like, everybody stop me if something's not working.
Do you think this will work on Python 3.10 or should I try to upgrade?
Try. Yeah. My only worry is that I think that there are older versions that are supported on the Intel Mac. So if you do get it where you got a wheel, it might be an out-of-date version. It's not going to do all that.
I'm on my Linux. I'm on Linux.
Oh, yeah. 3.10 should work.
Should work. Okay, cool.
Yep.
Interesting. Okay, so on the Mac, it could have worked on an older version of Python.
Yes, but yes.
Because I know I've had similar issues with SH tools.
Yeah.
And Yeah, and I did get it working.
Yes, SH tool, yeah, we, actually, I now made SH tools a optional or, install because of issues I was having.
It's so tough to get us.
It's tough, but it mostly works now. I think they made some updates last summer.
Okay.
I know Mark pretty well. I actually really like SH tools.
Yeah.
Okay,
Yeah.
let's see. Oops. There we go, okay.
Okay.
And this is the directory you want to put it in?
Yeah. How'd you?
Let's see, show either.
Yeah. I think if you just type this, hold on. Have you done that?
This no.
Okay, now you can follow the steps and it can be good.
Thank you.
So start with the activate and then the pip install.
I guess he hasn't talked through that yet.
Okay, so the farthest I'm along so far is we've installed
This step,
Jupyter Lab.
okay, perfect.
And now we need to create a kernel so that Jupyter Lab, when we open it up, it knows which Python to use. So that's where you create this. And I just create a kernel that's just with a name that allows you to identify it with this.
I see.
If I prefer to run my Jupyter environments in VS Code,
It's fine.
that's fine.
This is not a strict, this is just like,
Yeah.
I know this works.
Yeah.
I've tested it thoroughly, but if you are comfortable and you can sort of set up your own environment however you like. Once we get to as long as you can say pip install Swiftest and you don't get an error, then I'm happy.
I think, okay, so on
Or
three ten,
import Swiftest in your Jupyter notebook. That's kind of what we're getting to.
Yeah.
Okay, so I'm gonna, now I always like, my students know this, I always like to walk through arguments for shell commands. I'm a big believer in like, you really ought to know what things mean rather than just memorizing steps. I had too many students who have memorized 20 different like commands to do, and then they don't know what they mean. And so if things go wrong, they don't know how to adapt. So I think it's always, I love working in the shell. I'm kind of an old fashioned guy that way. I'm like probably the few Linux users who navigates without Finder and just opens things up at the shell. Yes, got an issue?
Sorry, the environment activates not.
Oh, it's because of your shell. Let's try it. Let's try it.
good.
No.
Yes, that is.
Source is not a H. Okay,
Okay,
I could actually, what I might do is
Yeah, if you reopen your,
I replace.
where are you? So make sure that you're inside
What
the,
shell are you using?
inside the folder that you have.
Honestly, I
Swiftest in.
can't remember what it is.
T shell. Okay.
I was working with
Is that
Eric's
I'm just in my-
student,
Where did you run
Steven
the
Schwartz a
main?
while ago.
did you run
Okay.
the,
Like the
It's
shell
just a
I-
weird non-standard shell. Okay,
Yeah, that's the
so
shell I stayed with.
It's been just,
Yeah.
is that where you get installed everything?
conda environment.
Maybe it was just.
Where did you?
Yeah,
I
Oh,
think
it should be
it's
there.
fine. Because when I ran just from within this,
Where is your?
there we go.
But you did the
Yeah,
GitHub
so-
thing, right?
yeah.
Again, I'm gonna explain what it is. So
Yeah.
you were in T shell.
But
All I did was
why is that
activate
not-
Z shell because that's the one I use. That's actually the default shell for.
Why is there,
Okay.
when you ls Swift,
I noticed over here that you had a conda environment automatically activated.
there's only source, why
My-
is there?
My experience is that
Everything.
mixing conda and virtual environments is a bad idea. So
Maybe
I
actually just-
deactivated your
You get
conda
the,
environment,
the-
activated your virtual environment, so now you're just in ENV.
to-
Now you can do
No,
pip install Swiftest Jupyter Lab and let's see if it works.
Okay.
Oh, you got the Swiftest branch, okay, go back to the tab page, yep, and then go to.
And then Jupyter Lab.
Because I just did.
Now that I'm standing back here, I can see that the text is a little small, so
You might be ahead.
zoom in.
Well, there we go.
Maybe refresh this page.
Yeah.
And then the downloading, collecting.
Right, things are installing.
Oh, I think,
Yeah,
It might have been
I
cast from the
project,
previous.
I was.
Yeah.
I left it in the
Okay,
shell.
that's fine. Just a good-
Even seemed like a guy
issues.
who would do some weird
But,
shell, like
I'll be-
some
I'll be
crazy
the-
thing that, yeah. I know, speaking.
I'll be that.
Yeah, I was working again.
Yeah, get going again.
Grab Stuff.
should I do it here or should I do it?
Yeah, well.
And he probably learned all
we
kinds
have
of things from Derek.
I don't know,
Griffin
maybe
last
keep
year.
your code.
Yeah, GKG drives also has its own quirky things to
Then
make it
feeding
work.
into the-
Because I have.
Okay, good. So now I do the IPython kernel bit there. How are we doing on the side of the screen?
I realized I cloned the wrong thing,
She cloned the Swiftest,
the whole thing, yeah.
Oh, yeah, instead of this page?
Yeah, so I'm redoing
Yeah,
it.
that's fine. Actually, we will clone the Swiftest, but not till after we get through the basics, because,
I
so
see,
now go ahead and do your git clone.
okay, so,
yeah, and it should be, I'll put the URL up again. It's hard to see on that screen.
okay,
Then,
then now
okay, CD into that.
CD into. So,
And then do the Python.
Yeah, now you, yeah.
3.12.
Sure, let's flash it out. Here, the space behind the.
Okay, you got the IPython kernel
Yes.
set up? Okay, I'm gonna just,
Okay,
while these folks get caught up, I'm just gonna do the next step, which is to
Then.
run Jupyter Lab.
Swiftest and Jupyter Lab.
Oh, before we do that, I wanna shell command.
Question about this, I've never had to run this IPython kernel install user.
Mhm.
And then name, line, what is that?
Okay, so Jupyter needs to have a kernel to know which version of Python and all the packages to use.
Yeah.
Because virtual environments are sort of local, you install them on some folder attached to your project.
Mhm.
They're not globally in the system. The Jupyter, when you run Jupyter, it's not going to know that there's a Jupyter compatible kernel in that folder. So what you have to do is you have to basically register your virtual environment with the kernel for Jupyter. It's like, the model for how virtual environments work, where you have a local thing such a project doesn't match the model for how Jupyter works, where you have one big Jupyter install and it kind of points to the kernels are available across the system. And so this is just a way of registering your virtual environment to Jupyter so that you can select it from the kernel menu.
Okay.
So, oh, by the way, if you ever seen the ampersand at the end of a command? All that means is that it will run the command in the background, so it won't take over your terminal. It'll still be running. It'll just allow you to use your terminal still. That's all that does. So it kind of keeps it running as a background process on the terminal. So I like to use it for Jupyter Lab. That way I can just go back to the terminal if I need to use it for something. Okay, so in my system, it's going to automatically open it in Firefox, and we should see, I've been messing with stuff, so I've got everything open. So should see something that looks like, no, should look more like this if I hadn't been running.
says I don't have the module IPython.
So I just do git install.
Oh, did you install Jupyter Lab? Because IPython kernel should have come with that.
Yeah, because I just did pip
Can you-
install.
Let me see.
I'm not convinced you're on your virtual environment.
Yeah, let's see.
Let's double check.
You are.
Okay.
So,
Python kernel.
well, that's unexpected. What did happen?
Oh, I think it's
You've
just
got
cloud,
some,
yeah,
you've got some hotkey that I don't,
yeah.
everybody's
numbers is-
machines are different.
Yeah. It's going to.
You're gonna want to re-enter your virtual environment when you get there, I think.
Yeah.
Yeah. Nice thing about if we switch to VS Code, all this kind of happens automatically, but
Oh, I see, okay.
I
So we
wasn't
just. gonna
sure I
do-
want to go that advanced yet, but yeah, dot space DNV slash bin slash activate.
That's why I felt different. I always do source bin.
Yeah, well, depends on your shell. Source is a bash command, and I
Yeah.
use Z shell, so dot is the more general one, but then apparently T shell doesn't have it, so it's like, okay, so, sure, pip is the right one. Yeah. Let's see. Got IPy installed. Oh, you know what? What was, no, I've forgotten, like my own command.
It's this one right here. This one?
IPy, yeah,
IPython.
oh, I know what the problem is.
Python.
It might be that. Okay, so IPython is installed.
Python.
No.
Stop.
Who knows? We had to.
It's so weird, okay.
Okay,
Okay.
now, that should open up in your default browser and we should be seeing, yes, good, okay. Cool. So they already got their Jupyter notebook up on the screen like this?
Yeah.
Okay. You'll see that in the menu options here, the tap Swiftest kernel shows up. That's why we have to do that kernel thing. So we get access to that. All right, so what I want you to do is we're going to go start with the basic simulation. So if we go to the basic simulation folder, you should see the basic simulation notebook. Now, the notebook basically has all the, we don't have the outputs yet. We have all the steps here. This is mainly so I can kind of go through sort of how it's structured, how it works, and show you sort of really basic examples of how to get going. But this is just a starting point. And at any point, you know, everybody here, I'm hoping will want to use our code for something. So if there's like a use case or a question you have about something, we can play around with it. It's the beauty of Jupyter Notebooks. We can try things and see what happens. And I will say that even though I'm the head developer, and I've been working on this since 2019-ish, I still I have to refer to my own documentation sometimes for API stuff. Sometimes things don't work the way I thought they should, so we'll see. I know that this works. Okay. Turns out this first line here is obsolete as of last week. So I actually fixed this problem. Okay, let's talk about what Swiftest is first before we kind of get in. Now we've got it. Oh, you know what? I want to make sure that we can actually, we've got the preliminaries done. So I want you to activate this cell, the import Swiftest cell, and tell me it shows a number 1 here and not a big error warning. Okay, we got number 1.
Oh, God.
Yeah, it depends on your system. Sometimes it's got to load all the junk up and. Uh-oh.
But it hasn't felt
Okay,
yet.
is that one?
Good. All right, good. All right. See, if we had more than 3 people, we wouldn't be here yet. Okay,
Question?
so who here has ever heard of a symplectic integrator before?
You got a question?
Oh, yes.
How do you, sorry, what did you do to do that?
Oh. In Jupyter Lab, you just hit Shift Enter.
Oh, okay.
So, yeah, you got it. Yeah,
Okay.
you basically just ran that cell.
Okay.
That's all I really meant.
Okay.
I said activate, but I meant just run the cell. We're not doing it. Okay, who here has heard of a symplectic integrator? You've heard of a symplectic integrator, so 1 out of 3, that's not too bad. Okay, you want to tell us what you think a symplectic integrator is?
Yeah, I'll tell you, I'll tell us what I think it is.
Okay, have you taken a class from Renu Malhotra?
I have.
Okay, so
That's one.
Well,
you took it too, but you're still in the know, right? Okay.
She didn't care too much about Embody or she wanted us to learn, you know, the analytics of this stuff.
Oh, yes, of course, right. When I took her class back in 2005, we actually had to write a symplectic integrator.
I think we only had to do a leapfrog-esque integrator.
Basically, yeah,
Yeah.
it's the underlying algorithm for the Wisdom-Holman mapping.
Yeah.
Symplectic integrators is a leapfrog, leapfrog ODE solver.
So, okay, so then maybe my memory is incorrect. I believe so when it comes to orbits and orbital dynamics, there are certain geometries, like in the two-body problem, you know that the orbit will be elliptical for both bodies. So a symplectic integrator takes advantage of this geometric attribute to in an advantageous way for the integration. So that way you don't need to like Runge Kutta, which would be another type of integrator of forces, would just time step forward, figure out all the forces and accelerations, velocities, and so on, but wouldn't necessarily stay true to the shape of the ellipse, at least not as perfectly. So if you know that something's supposed to fit an ellipse, you can take advantage of this. Of course, this doesn't fully survive in more than the two-body problem when you have multiple bodies and no orbit is ever truly elliptical like in that, but you can still, I believe these symplectic integrators still take some account of the geometry, and this helps them for long-term integration stay more energy and angular momentum. It just keeps the conserved quantities closer to conserved than numerically.
That's not bad. It's a little incomplete, but not bad.
Thank you.
It's good. Yeah. So I'll give you a historical perspective on it, because I actually know the people who sort of worked all this out are still working in the field. I saw one half of the duo, I saw Matt Holman at a conference not that long ago. So these people are still around. So let's take you back in time to the 1980s and the era of long stop Uranus, the Voyager encounters. My advisor, Radium Ultra, was a grad student at Cornell, and they were trying to do numerical integrations of the Uranian satellites in preparation for the Voyager encounter. And at the time, the best integrators were things like long stop. There were Buller-Stower integrators were out there. It was in the numerical recipes book, so people were using that. But the problem that people faced in things like modeling the long-term dynamics of the solar system, which is something that Jack Wisdom had been working on in the 80s. What are the, how chaotic is the solar system? What are the long-term like orbital elements of all the planets do over billions of years? And the integrators at the time were not very good at going for very long times. Computers were not as good. But as you said, like the way to sort of approach the n-body problem is to take the equations that govern the forces, like the basic Newton's gravity. All the bodies in the solar system are perturbing each other through Newtonian gravity. And so to basically integrate this equation of motion is to take the positions of all the bodies, calculate the perturbations, the basically gravitational attraction between every single pair, including with the sun, march forward in time with basically you apply those accelerations to your velocity vectors, velocities march in time. So given some initial conditions of the position of velocity vectors, in a time step, you compute the accelerations and you move forward and march forward in time. It's pretty standard sort of time marching out techniques. But the problem is that the solar system, now this is a thing that if you're an astronomer, you're like, they don't use these symplectic, they don't have the kind of problems we have. Like, how old is the Milky Way?
How old?
Yeah.
Man, we're in the astronomy building and none of us. It's gotta be older than 4 bill.
Yeah,
That's us. Solar system
Like
4
that.
billion.
isn't it like 13?
13 is the age of the universe.
In what units?
13 billion years.
Yeah, 30 million years. Okay, the way I think of it is Milky Way is about 40 rotation periods of the Milky Way, right? So the dynamical time scale of the Milky Way is not very long. Like if you think about how long it takes for a galaxy to rotate completely on one period, it's like
The Milky Way is
hundreds of millions of years, right? So the dynamical age of the Milky Way is pretty short. It's only about 40 periods old-ish. It doesn't, not 1-to-1 because the Milky Way is not like
That's insane.
Keplerian orbits, but that's basically the universe is actually, from a dynamics perspective, quite young, right? So when people are doing cosmology simulations, they basically can get away with stuff the solar system people can't, because how old is the solar system?
4 billion years.
Years?
About 4 billion orbits of the Earth.
Yeah, but we also have Mercury,
Yep.
which is like goes around 4 times faster. So it's really like 20 billion orbits old, right? So if you want to accurately get the orbits of planets, you have to basically, you're gonna be time stepping a lot. Now, if you're using one of these older codes where you're basically computing all the forces between all the bodies, like, you have to take hundreds of time steps per orbit to actually get a solution that doesn't have errors that grow larger than you accept. So you often with these older codes, you would set like a Runge-Kutta. If you ever used like in a class, you've learned like Runge-Kutta, there's like a epsilon value, there's a value of like the error tolerance that you're willing to accept, right? The problem is that the error tolerance is compound. So if you have to do the steps 20 billion times to get Mercury, 1/20 billionth of the AU in your error will compound over time, and Mercury's gonna drift off to some unphysically wrong orbit over that time. Now, unless you have to have ridiculously short small time tolerances or really small time steps to actually capture it all. So this meant that in fact, up until like the mid-90s, a lot of people weren't doing solar system dynamics with n-body. They were using things like Irpik methods, which is a statistical method developed by Jan Irpik in the 50s. So I had a colleague, Bill Bodke, who's a fairly well-known planetary scientist, told me that when he was in grad school here at Arizona, they had a DPS. It was the only time they ever did this. They did a DPS that was posters only, no talks. Yeah, the 2000, what did I say, 1994, I think, DPS they had here. This is like Mark Sykes' idea, I think, if I remember. So yeah, so they had this infamous like poster only conference, and Bodke was a grad student. He was just finishing up with Rick Greenberg at the time. And he had a poster on modeling asteroid orbits for like 100 million years. It was like he was really proud of this and using Irpik codes. And he went and saw this poster by Jack Wisdom that had like 1 billion years evolution of an embodied solar system. He was like, what's happening? And he realized after talking with him and looking at the poster that all the work he had done for his dissertation was now obsolete. Like the techniques he had used, he'd learned and spent years a grad student doing, were now out the window because somebody figured out a shortcut that made everything easier to do with solar system. And that was Wisdom and Holman, 1991, I think is when the first paper came out. The symplectic integrators, something called the Wisdom-Holman map or the mixed variable symplectic map. So there's a cute trick to it, and it's not, they didn't come with this whole cloth. There had been similar types of tricks employed before, particularly for like comet orbits. The idea is that it requires, I'm going to give you the sort of stripped down version because it involves Hamiltonians. And I don't want to go, it's like write Hamiltonians on a board. But let's just trust me that you can actually write the gravitational interaction between planets with a big Hamiltonian. It includes the sun and the interactions between all the planets. Now, the Hamiltonian, there's a term of the Hamiltonian that's common for all the planets, and that's the one that involves the sun. And that's the dominant component. But most, in our solar system, Jupiter is 1/1000th of the mass of the sun. So basically everything is really close to Keplerian, which is how Kepler was able to figure this out in the first place. It's like Kepler with like a little bit of perturbation. So if you split up the Hamiltonian for the solar system orbits, you got this great, humongous, big Kepler two-body looking thing, and then a bunch of smaller perturbation things, which are important, but much, much smaller. Okay, so the insight they had was that if you, by a particular choice of variables, actually a choice of coordinate systems, using a Jacobi coordinate system, you can write the Hamiltonian in that coordinate system, and there's a nice clean split between something that looks exactly like a two-body Hamiltonian and something that looks like an n-body Hamiltonian. The two-body one has an analytical solution. It doesn't have a closed form analytical solution, but it does have an equation you can write. It's the Kepler equation. There's no known closed form solution to it, but you use iterative methods and basically solve it almost exactly with whatever precision you want. So you can actually solve it, and basically that's what you said, the elliptical orbit, right? And then you have this perturbation part, the interaction part.
Yeah.
right? So the way it works is that you split the problem up, the Kepler two-body part and the interaction part. The Kepler two-body part has a known solution, so you can solve that part to arbitrarily high precision. And then all you have to do then is use a numerical method to compute the interaction parts. But because the interaction parts are so much smaller than the sun, you can get away with much larger step sizes in order to get the same precision out of that. So it allows you to take great big steps and not lose too much precision. Rule of thumb for these, which is important for our setting up simulations, is you want your step size to be about no shorter than about 1/20th or 1/30th the orbital period of the innermost body. So if you got Mercury in your runs, 88 days, you keep these numbers back here. 88 days, so 1/20th of that is about like 2 or 3 days, something like that. So a two-day time step is good enough, kind of, gets you 2.5 day, 3 days time step. Okay. Versus the older methods, you might have to, in order to gain the same precision, you'd have to like take, hour-long time steps in order to get that same precision. So it was really, really great. And the use of the symplectic mapping meant that there was all these symmetries in the problem. That one of the results of that was that the energy of the orbits doesn't change with time. You don't get precise energy, so you wouldn't use these codes for spacecraft navigation, because you will actually have errors in the energy, which translates to like semi-major axis, like radial distance of your bodies, but those errors stay bounded. It means you'll have errors at each time step, but they don't compound. They stay bounded within a value. And that's really what makes these useful. I can run Mercury's orbit for 20 billion orbits, which is 20 times 20, 400 billion orbits. And I can be satisfied that the orbit I get at the end is within some tolerance of Mercury's orbit. Like it's not going to spiral out or in due to energy drift. That's basically what energy drift does. It makes you spiral away or inwards. So they become the workhorse of solar system dynamics. So there are a couple, there's some alternatives. There's a guy who, I think he's a SETI or somewhere out the West Coast who doesn't like them, but he's an oddball. So if you have ever used rebounds, a lot of theirs use symplectic methods. Yeah, Hano does things other than solar system dynamics, so there's some other algorithms in there. But the Mercurius, if you've ever used rebound, Mercurius is the symplectic integrator. Swiftest, Swifter. So the heart of Swiftest are these symplectic integrators. In fact, the older Swift, which is based on old Fortran 77 code, has a bunch of the other older algorithms, like the T+V, which was another Hamiltonian splitting. It was often used in the 90s. Buller-Stower, a bunch of other things. I don't even bother with those. I only use the symplectic ones. So it's really stripped down to really four techniques that are used here. Okay, so that's what these codes are. It's a symplectic integrator. There's actually 4 integrators built in. We'll get to that in a bit. Okay, so I mentioned rebound. How many of you have used rebound before? All right. I'm kind of swimming upstream a little bit with my code, because if you go to any conferences with dynamics, rebound is taken over completely. Rebound is easy to install, easy to run. There's very sophisticated code, does all kinds of things. Doesn't do everything. That's why there's still a niche for us. But I was actually inspired by rebound early on, so I actually adopted some of the structure of code is based on rebound. So if you ever use rebound, you'll see some familiarity. It doesn't map one-to-one though, and it's something I need to do is, have a guide. If you're a rebound user, you do this instead of that. But the basic level, you kind of set up a Swiftest simulation the same way you'd set up a rebound simulation. Okay, so a Swiftest simulation begins with building a simulation object. I almost always call it sim, unless I have more than one and I need to disambiguate them. So it's an object-oriented code. So there's a class called simulation, which is what holds everything. So if we run that cell, you should see some output to the screen. This is just giving you, okay, so I'll step back a little bit. Swift, Swifter, and Swiftest are all part of a family. Swifter is what I used when I was a a postdoc at Swery with the people who wrote Swift. There are Fortran-based codes, and they do certain things a certain way. I tried to make it sort of backwards compatible and sort of for anybody who's familiar, like Hal Levison or Bill Botke, who've used these codes before, or even this morning, it does a lot of things very similar to the way Swift did. So one of the things is that it shows you these sort of the sort of run conditions. So there's a bunch of default sort of parameters that are set by a simulation object, and it's basically just printing out what those are. Okay, we'll get to those in a bit. There's they're plenty documented, so I'm not going to belabor them right now, but just know that it begins a simulation with a set of defaults, and then there's some things you want to modify as you go along. The first thing, obviously, is we want to put some planets in or some bodies. We don't have anything in our simulation to run, so we need to start some planets. Now, one of the things I really like about Rebound, one of the first things I tried to sort of recreate was the ability to call up real bodies quickly. So I interface with this JPL Horizons system. So the JPL maintains all the ephemerides for planets. And so I have a method that sort of tries to use some bit of fuzzy logic and fetch bodies that you want. So a really standard use case is to call up, the major planets of the solar system. Sorry, Pluto. So we can do that. And you'll see some of the output. There's flags to turn that off, but ask me later and I'll show you how to do that. And it basically goes through and it tells you basically it's fetching the body from horizons. It tells you, it tries to find the best match. So you don't have to be really precise about naming things. So here, look for Mars and it defaults to the Mars Berry Center because there are also Mars Body Center. But for n-body dynamics, you want to use Berry Center values for things. And puts them all in, tells you the ID that it used, whatnot. So these are all things you can alter if you wanted to. You can actually be more specific. And I've tried to adopt the model of everything is easy to do with a set of reasonable defaults. And then anything you want to modify, you go to the documentation page and figure out how to modify it. But I want it works without you having to do much other than say, I want the sun and Jupiter. And then you ask for the sun and Jupiter and it goes and gets it. Don't worry too much about the details. Okay, so I mentioned that these are symplectic integrators, and it will allow you to set any step size you want. These are fixed step size tools. People have tried and failed to make multi-step versions of this. The problem with symplectic integrators is the symplectic nature of them is very fragile. So almost everything you do to them breaks it. And so that limits your ability to do a lot of things that like galaxy cosmology people do. I'm not going to go through this too carefully, but there's some ways of sort of setting up things like how much output you want to do and how much time steps. I'll just focus on this here and kind of tell you what each of these arguments does. So at the sort of minimum required set of arguments you need to pass to a simulation to get it running are the stopping time, how long you want to run the simulation for, and by default, the unit system is AU, year, and solar mass. Those are the default units.
G equals
G gets computed internally for you.
But in that unit system, would that be G equals 4 pi squared or G equals 1?
I think so. Yeah, we can actually call it up. I don't remember how to do that.
I'm just thinking rebounds default is G equals 1, which makes time equals 2 pi, I think. 2 pi years.
Yeah, you can set all these things. Like I said, I don't always remember how. Oh, you know what? I know something about. Oh, I think G might have been printed out here. Scroll back up. No, it shows the units, but not thing. There is a. There we go. Yeah, GU. G and okay, yeah, G and the system units. That's what the U means.
4 times 3.1.
Yeah, so that's 2 pi. So it's 4 pi squared is that. Yeah. Yes, so there are a bunch of options. I would refer to I almost always keep things in the default units. My student Costa, who does a lot of stuff with Mars moons, has a custom unit system that he sends where it's like Mars is 1 and the mass of Mars is 1. And the only reason you want to set the units differently than the default is there's just a best practices when you're using numerical things is to try to keep floating point numbers reasonable values. So why you really shouldn't use like SI or God forbid CGS units where everything's in, the distance to the sun is in centimeters, because those are enormous numbers and you start multiplying lots of big numbers by small numbers and big numbers, and then you basically are at risk of having floating point nonsense happen. So you want to set up a natural unit system that's kind of close to things being around, within a few orders of magnitude of 1. And so MSUN AU year is not a bad set of natural units to use, right? Okay. Okay, so I'm gonna. Okay, so you want to the default unit system is years, so I'm doing 100,000 year simulation. Now I'm going to take a 0.01 years time step, and that's what this says up here is we've got Mercury in the system, so we want to make sure we capture it. Now, there's 2 arguments here that are a little bit more obscure. One is T-step out and dumb cadence. Okay, so let me tell you about those quick. So the thing with these integrators, I said that the thing that these are doing are these solar system problems that take just god-awful large numbers of steps. It's very rare that we actually care about the intermediate steps, right? I'm going to be taking, if I take 100,000 years, I'm going to output every 0.01 years. That means that for this little 100,000 year simulation, I'm going to be stepping the planets 10 million times, right? And so if I wanted to store that output and look at it later, that means storing 10 million floating point values for every single thing that we store. It's a major axis, eccentricity, inclination, Cartesian position, velocity, and it gets out of hand really quick. And there's very few applications where we need that fidelity of data. So one of the things you want to think about when you're doing a problem is how much output do you want? You want to have enough output that you're capturing. You don't want to be, because the thing with these codes is once they run, they're going to run and intermediate values will be thrown away. So you want to make sure that you want to save data at some cadence, right? Some amount of data. You want to make sure it's enough data that you can do something and have the fidelity to do the problem you want, but not so much that you're filling up your hard drive with a whole bunch of positions and velocity vectors of planets that are every couple of days or something. Yeah.
Then as far as data output goes, another consideration can be that it also slows it down. Is that
yes?
Correct?
Okay, so that's where this dumb cadence comes from. All right. So one of the thing that actually makes Swiftest one of the things I think is a comparative advantage for Swiftest versus Rebound is that Rebound, Kano has this very strict rule that Rebound never needs dependencies. You can compile Rebound with the C compiler and the source code, and you don't need any libraries or anything to run it. Yeah. It's a commendable goal, but one of the issues is data storage is this custom bespoke system.
Yeah, it's been archived thing.
This SIM archive thing, which you need to use Rebound tools to actually access.
Yeah.
I decided to take the tack of I would rather use a standard set of libraries for storing data that has enough sort of infrastructure to useful. And actually some colleagues of mine in my department do climate science and climate modeling, and the climate people figured this stuff out back in the 80s. So there are actually these high performance storage systems that come out of climate data that are widely used, well supported. There's libraries in Fortran and C and Python, and there's all these tools. And so they told me, just use that. And I say, use that. And I've been using it ever since. So the format that we store things in is called netcdf. There was about 10 years ago or so, there were actually used to be 2 data storage systems, netcdf and HDF. And netcdf4 and HDF5 merged so that basically netcdf4 data is actually stored in HDF5 format. So they're actually compatible with each other. So if you ever see, this is used a lot in astronomy, so you may come across it. Actually, I know one of my students came across this quite a bit in dealing with telescope data.
Most of our SPH data is an H5 part or
Yeah, okay, so if you're feeling this, same thing. So we use the same thing. Although it's stored as a netcdf, so .nc files, but it's under the hood, it's still H5. With some different metadata to help netcdf know what to do with it. But in Python, I actually use a tool called Xarray for doing the data processing. Now, to me, because I didn't want to be, Pato really likes algorithms. He's a great scientist, but he likes digging around and like getting, and he's done some really fantastic work with it. I did not want to write my own custom bespoke output system. I already was dealing with that with the old codes, which were storing things in binary Fortran files. And yeah, so it's just a mess. So I wanted to just pick a library that like people use and I didn't have to think about it. So I used netcdf and Xarray. But those, they're very sophisticated and they allow you to do some really, really cool stuff. I'll have some demos of some of the stuff you can do to do your data analysis really quickly. So that then having it in that format and all the tools at your fingertips, there's a huge ecosystem for doing data processing with these tools, primarily through Xarray, what I use. And you can do so much cool stuff with it. But the ability to do that cool stuff means that the files themselves are kind of complicated. You're not just dumping raw numbers to a file. There's all the structure down in the bowels of it. So if I was to output my, even if I was to output every 1,000 years in a simulation like this, I'd be spending most of my time writing to a file. And I don't really need to do that. So I have a little trick to do is that when you have really short runs like this, where it's only going to be like 100 outputs, got the planets, it's not going to be very much data. There's a thing called dump cadence. The dump cadence tells you how often in one of these steps I'm going to save. So if I had dump cadence was 1, that means I'm going to be writing to a file every 1,000 years to 100,000 years. If I put dump cadence 2, that means I would be outputting every 2,000 years. So I'd store the data in memory, the 1,000-year step, the 0-year step, the 1,000-year step, and then when I got to the 2,000-year step, I would dump it to the file, both 1,000 and 2,000. So it kind of holds everything in RAM up to the point where you're ready to dump it and it dumps it out.
Interesting. Okay.
Yeah. And so, and it actually is what if I do say to myself, it's rather clever. It actually stores like a memory snapshot of the data. So it's actually purely the data, like there's no difference between the data stored behind the scenes and what gets written to the file. So this makes this exactly bit identical data, no matter what value you picked on this, right? So dump cadence 0 is the case where it keeps all the data in memory until the run ends.
Yeah.
Then it dumps it out. That's useful if you got a short run that you're not going to blow up your RAM, your short-term memory on your machine. And so you just store the entire run in memory. And then when the run's done, then it's going to dump it to file. And it's a lot more efficient to write the whole data set to file than to do it for every single time step, because there's all this netcdf and HDF5 infrastructure to figure out what time you're in. And if you do it all at once, it's just much more efficient.
Okay, that's really interesting technically. I think I had another part of this question was a bit more analytically. If I remember how the Hamiltonian stepping works, it's in this like half time. If you know what I'm
Yeah. So
and so when you're talking about like when you're trying to print out or access, at least with Rebound, when you're trying to access in units during this halftime, you need to actually converge things.
Yeah, I know what you mean.
Asking. Yeah,
I know what you mean. It's actually the way it works, and because when I built the underlying, we converted over the original Swift and Swifter code to this object-oriented Fortran. There is such a thing called OOF.
OOF.
Yes. I tried really hard to make sure that the sort of algorithms work identically to the older code and actually go through and make sure they're bit identical outputs as much as I could.
Yeah.
So what the shortcut they take is that you take a half step first, but then because so there's a half step, it's a kick, drift, kick algorithm. So
Yes.
Kick is the accelerations, drift is the Keplerian part, then you kick again. It's a half kick, full drift, half kick.
Yeah.
But then you do a half kick again, so that ends up being like a full kick.
Yeah.
On the second time around.
Yes.
So actually there's a bunch of parts in the code that are a little different. Like if it's the first time through the algorithm, you take a half step.
Yeah.
And then after that, you take a full step.
Full.
Because it's. So you're only ever, you don't have to worry about half steps or anything. It saves things at the full step.
And then when you need to, okay, the save season, the full step, but then, I think, it's thought that there's a problem where if you wanna output, then you slow things down, cause then you need to go back a half, then you output, then another half, and then another, then it gets into its full. So you can just bog things down by making it right out.
No, it's a lot simpler than that. Basically, there's a dump step that occurs at the end of your DT.
Yeah.
Every integer times DT.
Yeah.
There's the chance for storing.
Okay.
Okay,
All right.
so in fact, we can even look at the output. So let's just run this.
Sure.
So if we run that, okay, that's its parameter. I'll say actually another thing too is I try to make this flexible so that you can either set run parameters like this through a set parameter method, or you can just pass the same set of arguments through the run method and it does the same thing behind the scenes. So so I can actually do, oh, I got rid of the run. So I could actually just say this as run instead of set parameter. I got rid of my run because you were asking a question.
Sorry.
That's all right. Okay, so we're gonna run that. And it should be printing out to screen. This little it should be running. Takes a while. It's because in 100,000 years.
Running a Swiftest ever run from T to 100,000
Yeah.
with one thread.
Yeah.
And it's giving a nice,
Oh,
I
yeah.
like that it's giving a nice automatic,
Yeah, although one of the things I like to do is actually do a little bit better job outputting. This is a little bit on the hokey side. Seems slower than it ought to be, honestly. I wonder if I accidentally,
mine's running pretty fast.
okay,
Um,
I wonder if I accidentally put a debug.
I'm at 900,000 and finished.
Yeah,
Yep.
a lot faster, mine's still going.
Green, well, I'm on the Mimus.
Yeah.
Oh, you're on a cluster, okay, yeah.
Well, it still was only on one thread. It shouldn't have been that much.
Yes, okay, the thing about the threads, I told you there was a little thing.
Yeah.
Okay, there we go, I restarted the kernel, for whatever reason that fixed it. I wonder if it was something with running in the background. Okay, so thing about threads. One of the, I said in my talk that one of our goals was to make the parallelization work. You only see the benefits of parallelization, of the OpenMP parallelization, when you have a large number of fully interacting bodies.
Yeah.
More than really more than about 1,000.
Yeah.
But I basically built in a check that if you have less than 100 fully interacting bodies, it shuts parallelization off. Because you'll actually go slower.
Yeah.
So if I did 2 threads here, it would actually go a lot slower than 1. So you'll only ever be the number of threads, you ask for if you have like 100 or 1,000 bodies, then you take advantage of parallelization. For this kind of solar system problem, one of the things is like really want to do. Hano showed off at DDA a year and a half ago. They used SIMD to, if you have exactly 8 planets, you can get like massive speed up. But only if you have exactly 8. Which
Right.
like the solar system, because it fits in this like 8
Two to the-
this, yeah. It just fits in this SIMD thing. Is it just basically just all these computations all at once. Anyway, someday we'll get that. All right, so it should run, and it's gonna gives you some output, tells you that it's output 101 steps. And I'm gonna switch gears a little bit. So we're gonna look at the data in a minute, but I want to show you all the data gets stored in a folder called sim data. I want to show you what it is. So this includes all the data. So one of the things about Swiftest is that you can also run it from a command line, the way you would run the old Fortran code. And so this is all the kind of stuff that you'd see in a Fortran output. So the actual run data is stored in this .nc file, but also has like a log file that gives you sort of an output. And it has a lot of nice information. It will tell you sort of, it gives you a header that tells you what were the initial conditions, what are the settings that were set for this particular run. So like a record of all the things. Tells you all the options that were used. And then it also gives you a running tally of the amount of time it took to run the code, the amount of time that's in seconds, the amount of time it took to run a single interval, and how many bodies were in the system, how many were fully massive. So 8 fully massive planets, because we actually do have a category of body, it's called semi-interacting. Rebound calls them massive test particles, which I think is a really funny name. They interact with the major bodies, but not each other.
Yeah.
And then test particles, no test particles in this. It gives you a running tally of the error and momentum, angular momentum, error and orbit, the different flavors of error, the orbital error plus a total, because if you have collisions or losing particles, you have to bookkeep that error. And as a check, make sure that we don't lose mass. This should always be exactly 0. Kind of a leftover from when we were troubleshooting.
I have a different version of this log. I have Swiftest 2024 12.1.
Oh, okay, interesting. Can you do pip install upgrade Swiftest
Sure.
on your terminal?
Yeah.
I mean, it's fine. I don't think much has changed since then. Fraggle has changed a bit though, so.
Mhm.
Did you install from source or did you install it from pip install?
Pip. But I did it from 3.10.
Oh, I wonder if we deprecated 310 and it's now 311 is the minimum.
Yeah.
This is a problem with this kind of code is it got to keep up with the industry. Right?
Yeah.
Yeah, when Python versions get deprecated, all your tools stop working in those versions and it's like, it's hit or miss.
Mine's 2025.
And, it didn't finish though.
It's not, the simulation hasn't finished though.
Oh, really? Huh.
Yeah, it's still going. I don't know why it's so slow.
You probably, I wonder if it's just older computers. I almost always, when I'm doing runs, I do it on a cluster machine, not
Yeah.
my laptop. I use my laptop for debugging and troubleshooting, but not for these kind of runs.
Yeah, all the computers in Eric's lab run a lot of our SPH simulations, so.
So I think for illustration purposes, it's
Yeah.
fine to use your laptop.
Yeah,
Do what he's doing when you want to actually use this for something.
yeah.
That's okay. So let me, I'm just gonna, as you're finishing that, I'm just gonna talk a little bit about some of the options you can do. So I've just giving you some examples of how you can submit options in different order and things, and they all run fine. So let's look at the data now. This is where I think we're really shine is the data comes at you prepared for analysis. There's very little you have to actually do to get it. So one thing we do is we load up what's called an X-array data set. Has anybody here actually used X-array before? You know what I'm talking about? A little bit?
I know about it, but I actually haven't used too much about it.
So I will say that this is probably if you are not planning on being a developer or contributor and dig into the Fortran, this is going to be the most challenging part about using Swiftest because there's a bit of a learning curve to using X-array. How many of you have used pandas before? Okay, how are you with pandas?
I use it.
You've used it.
I've only put it into my code.
Okay, all right. So not a pandas power user in any, right? Okay, so the thing that got it to me to click what pandas is, because X-array is built on top of pandas. Pandas is Python's package that represents like a spreadsheet. So pandas data frame is basically a spreadsheet. It's like having an Excel spreadsheet, but not visual. It's all accessed through methods and function calls. So that's you have rows and columns, and you have these rows mean these things, these columns, you do operations that cross rows and columns, right? So X-array takes the pandas data frame and built something called there's two constructs, the data array and a data set, which take something like a pandas like spreadsheet thing, but label everything with human understandable names for things. So rather than having column 0, column 1, row 0, row 1, you actually call things by their names. And it's a lot more human friendly to deal with, right? So, so this is the data you get from a simulation. And there are basically 3 parts to it, and they helpfully in their little Jupyter thing break it down for you. There are these 3 things: dimension, coordinate, and data variable. And when they're bolded, that actually means dimension coordinate. That took me a while to figure out what those differences are. Okay, so let's take this apart. So the data we get has 3 coordinates to it, right? So, or sorry, 3 dimensions. So your dimensions are your axes, X, and Y. So in pandas, these would be the index, I, J, K indices, right? So this is a 3-dimensional data structure. 1 dimension is the name dimension. Name is just the name of the particle. So we index things by their names. So you could call up the Sun, Mercury, and Neptune by its name. You don't need to know what index value you're in. There's a time dimension. So every output time step, including the 0. So it's always 1 more than the end step because it saves the initial conditions for you. And there's a space dimension because there's a lot of vector data, like the position and velocity vector are or basically have a space dimension. So so these are dimensions of the coordinates. And you'll notice that the dimensions also appear in the coordinates. They don't have to. There's a lot of really great examples and stuff on the X-array website, so I'm not going to belabor it too much. But you know that the way this is set up is these are what are called dimension coordinates, which means that the dimensions are the indexes. Like there's a name, there's a 0th name, first name, second name, third name. We attach a variable to it to give the meaning. So the 0th index is sun, the first index is Mercury, the second. So that's how you make that connection. The dimension, if they were not bolded, they would have to be 0, 1, 2, 3, 4, right? So we give them meaning by attaching them to a variable. Okay, and then you can see these are called data variables. Each one of these is actually what's called a data array. So it's actually a simple. Basically, it's a little bit different. Like pandas, they have data frames and series. It's a similar kind of thing. This is like a series in pandas, and the whole thing's like a data frame. They're kind of sort of compatible. There's actually tools to go back and forth between them. You lose all the metadata. Okay, so these are the variables that are attached to the data set, and what the little thing here in parentheses tells you is what dimensionality it is. So the ID, which is it's actually what the Fortran code used to figure out which variables are. They're actually there's a numerical number that's attached to every bodies. You don't have to worry about it too much. Just know it's a one-dimensional variable with a name dimension. Status, that's a code that's you don't need to worry about. It's stored internally. You have NPL, the number of planets, the number of test particles, and the number of massive planets, so the fully massive bodies. And you can see that they go by time, so you can actually see how many bodies in a system. And it's always 8 because we haven't lost anything or gained anything. So there's going to be 8 across and 0 across. Particle type, there's a text that tells you what kind of body it is. Really useful for extracting things out. And then this is all the data you get. And by default, you always get all of this data. Internally, the code is tracking the position and velocity vectors. Those are what the integrators are actually doing. When we go to output that, everything is converted to orbital elements. So you have both. You always have both. If you ask me about this, if you care about GR, just know that there's a variable that the symplectic methods that do GR, they redefine time and redefine velocity. You have to track that in order to restart runs precisely. Then you have the same major axis, and this is in AU units. If it's not, so the sun doesn't have these values, so they're not in numbers. You can see you got Mercury, Venus, Earth, Mars, so on and so forth. And then you have lots of other things too.
Does the sun also not have positions? What's the
sun is by definition, its heliocentric velocity and position vector are 0. Actually, I don't know. Do we even store it?
You output everything in
Heliocentric, yeah.
rather than
not barycentric.
Joby or okay.
Yeah.
Okay.
It's easier to convert those if you need to. There's some built-in methods for doing that, but with storing heliocentric, it's much easier to deal with heliocentric everything.
Okay.
There's a ton of like metadata and stuff that could be useful. For runs like this, there's just not much. I will say that by default, when you use solar system stuff, it will try to fetch things like the J2 and J4. So the sun has a known J2, J4, so those get automatically put in there.
Yeah.
GR is automatically turned on. These are all things you can alter yourself if you want to. But by default, again, reasonable defaults, things are kind of make some sense, kind of most people's use cases with the ability to change them if you really want to.
So the simulation that we just ran did run included solar J2 and GR.
Yep. J2, J4, and GR. Yep.
Wow, so many more than I've ever done with rebound.
Yeah. And because why not? I mean, that's how the solar system works. Might as well just put those things in, right? If you call up planets, I think we got it set up so that if you ask for like Mars, it fetches a bunch of coefficients for SH tools. I don't quote me on that though. Kausa has been working on that.
Is that a rotation state?
Yeah. So we can get into that. So with the collision, the Fraggle, we have to track rotations, and so we have a bunch of rotation things. So the rotation rate and the rotation phase are both tracked of the central body. Only the central body is the rotation phase tracked.
I'm jumping ahead, but maybe. But since we're talking about data and data storage, how how modifiable is this if I wanted to attach an additional piece of data? Like, let's say that we were going from SPH to
Mhm.
body and we knew a body's core mass fraction,
Mhm.
just as a variable that we wanted to track. And let's say we added a prescription to Fraggle that modified the core mass fraction for every merger. Let's say if we were just doing a perfect merger run, and so it was a pretty simple task of
Yeah.
would I be able to track an additional variable like that?
Okay, so, not without a little bit of work.
Okay, there'd be some hacking
Yeah.
as well.
You would actually, so because the code itself is, what's actually running when you run this is a Fortran compiled library code.
Yeah.
And it's a lot like Rebound. Like Rebound has a Python front end, but if you make modifications, you have to go to the C
Yeah.
source code and actually modify and recompile it. Well,
Yeah.
you can get to that. I actually have a task for compiling the code. So yes, if you wanted to do that, you would have to modify the code to do that.
Okay.
So I could certainly help you. But
Yeah.
you have a pattern of how to do it.
Yeah.
Like Kalsta did this when we added when we started tracking like SH tools stuff and keeping the coefficients and rotation phase, like he did it. There's just a series of steps. It's a little tedious, but you have to create the variable in our netcdf library. And then on the Python side, you have to be able to read that in and structure it. There's a gazillion, all these things have that. You just follow you just copy paste and you just do what you did for like route phase and just follow that. That's all it is. Tedious, but not that hard. All right, so what's really beautiful about this though is the way you can actually do these sort of one-liner data processing to actually really quickly sort of visualize your data. So here, what I'm going to do is I'm going to plot the semi-major axis over time of all the things that are not the central body. So I'm going to select basically anything that's not a central body. That's all the planets with this X-array. So these are all X-array commands. Sim.data is the variable that stores the data set. And then there's a plot method. So I'm going to plot the x-axis will be time and hue, the color is going to be by name. So each planet gets its own color. And you can see one line, I was able to make that plot. Okay, well, we can go to the detailed simulation because I show you some more of the things that I think are useful, like setting up your own custom files and plotting, a little more sophisticated plotting. So anybody got questions about that so far? Other than Robert. All right, did everybody's notebooks run down and get that plot?
No, because my
Still really
simulation.
Still running, oh my goodness.
Yeah.
Shouldn't be that slow.
Not sure. I even restarted my kernel.
Takes about 10 seconds
per time set. No, that's slower than it really ought to be. You're on an M1, you're an M1 machine? Because I had an M1 not that long ago and it was not that problem. Okay, so I might need, I'm wondering if, okay, I think, what version of OS 10? Do you know what version of Mac OS 10, Mac OS you're using?
the most recent.
Tahoe? 26?
Yeah.
Huh. Oh, then now I don't know.
Yeah, Sequoia 15. And then I have the.
And I only just upgraded my operating system like a couple weeks ago, so. That's interesting, all right.
Yeah.
You know what we're gonna do is, I'll make note of that, and so I have some old virtual machines of old OS. Actually, I think I have an M1 somewhere in the house. I'll see if I can troubleshoot it on that. See why it's going so slow. It shouldn't be that slow. Okay. How many, what we could do is we could always expedite this. Let's just go to the detailed simulation setup because I think I start with basically something like this. We can modify it to be a much shorter run. It won't look as nice, but you'll be able to follow along. So just do 100 years instead of 1,000 or, something like that. Okay. Let's go to the detailed simulation. So this just goes in a little bit more detail about stuff. This is not a little felly thing I discovered that there's I'm just going to run this so that I have it all queued up. Okay, so one thing you can do, which can be really useful, is if you're running like multiple different simulations. I often do tests, like I have one of our test cases is I run it with GR, run it without GR, and I want to compare the two runs. So I run those in the same like project folder, but I want to make sure that the output data is in two different places. So you actually have an argument you can pass to store your simulation data in a custom directory. So by default, it's called sim data, but you can give it whatever name you want. So if you can create like two simulation objects on a project, and they can store their data in two separate folders and not collide with each other. So that's just one. And I will say the one thing that you can always do is every single method is documented in the API. So if you want to know what the full suite of options are, you can actually click on the API, click on simulation, and there's a very extensive page that tells you all the things that you can do to a simulation. And then there's the set parameter has the comprehensive list of all the other options that kind of control everything. There are set methods for every single sort of component of the code, but set parameter sort of consolidates them all in one place. And so this tells you things like how you set your units and how you set various other things that you might care about for more sophisticated ones. How you turn on GR or not, what collisional model you want to use, parameters for the collisional model, whether it's a restart, whether you're going to check for encounters, you know, all this sort of fiddly things that there are default. Everything has a default, but you can modify here. So the documentation page, pretty comprehensive. Try to keep it up to date. So like I'll show you a couple things, but just know that there's a lot of options out there to mess with the code if you have a use case a little different line.
I had an error on that for the X-array set option. That use new combined.
Comment that out. That's
Okay.
I just discovered that this morning. X-array has made some change that basically spit out a warning every single time you do a certain thing in the code. And so I wanted to turn that off. So just comment that line. It's not important.
Okay.
You probably just running an older version of X-array because it's an older version and
Possibly, yeah.
okay. So just comment it. I'll fix that when I get home.
Yep.
Okay. So again, I'm going to add all the planets. Okay, so now I'm gonna show you how to add your own bodies. Like you can add the solar system, and actually with the solar system, this is something that took me a while to get, but you can ask for just about anything that's named in the entire solar system, and it'll do its best to find it. Moons, asteroids, Kuiper belt objects, sednoids. If it can like match a string sort of reasonably to something that's in JPL. Then it'll try to do that. So like here, I'm just showing you how you can throw in like asteroids, and you can actually tell it as a small body because some asteroids have the same name as moons. They're like, there's at least one moon. I don't remember which one it is. There's Europa. There's an asteroid Europa.
Yeah.
Yeah. So if you ask for Europa, you'll get you'll get the moon first. I think you have to tell it's a small body, but typically it will just do its best. You can ask for Kuiper belt objects. You can ask for all kinds of things. Now, there's a couple little things of note that usually when you're doing n-body codes, like when you ask for the moon, when you ask for the Earth or Pluto, Earth and Pluto are special kind of worlds because they're really double planets, right? The Earth and Moon's significant enough that it actually adds enough mass to matter. But in a solar system, a full solar system simulation, you don't want to have the actual moon in there. That will actually doesn't work very well with symplectic codes because you'll have a close encounter case constantly, and you'll actually have problems with your code. So the way to get around this is when you actually ask for the Earth or Pluto, what it does is it fetches both, in the Earth's case, Earth and Moon, puts their masses together and initializes the center to be the barycenter. If you ask for Pluto, does the same thing. It takes Pluto and Charon, combines their masses, and sticks that body at the barycenter. Right? Those are the only two bodies we do this for. Okay, so you just got to keep that in mind that Earth and Pluto are special cases that, again, reasonable defaults. Most of the time, when you're doing a long-term solar system simulation, that's good enough, right? We don't really care about the moon as its own world. We just care to make sure that the Earth's orbit is doing what it's supposed to, is perturbing everything else the way it's supposed to. And if you don't have the moon, your perturbations will be off a little bit. When I was in grad school, it was really common not to have Mercury in your simulations because it just slowed everything down and usually didn't matter. And the way to do that is you can add Mercury's mass to the sun and you get more or less the same potential. So it's a common trick for expediency. And I just baked it into the code. If you want the actual Earth, there's ways to do it. I documented it here. So if you actually want to ask for Earth, you call it by its ID. I think it's 399, and you get the Earth body and not the Earth, not the combined Earth Moon. Okay, so that's just a little aside. The other thing too is you can actually create your own bodies. Typically, you build a collection of initial conditions out of NumPy arrays and just feed those into Swiftest. So here I'm going to create 5 massive bodies. I'm giving them a density, and there are some parameters that are stored for if you need to convert units. Like if you know something you want is in 3,000 kilograms per meter cubed, you can basically use these built-in conversion values to convert. And I think that I even made it, I need to update this, but I think that you can actually do kg to mu, go the other way, but I'm going to divide out. Fix that. So in this case, I'm making semi-interactive bodies. These are bodies that only Simba, the integrator Simba uses, that have mass, but they don't interact with each other. They only interact with the major bodies in the system. Often we use this for like modeling planet. In the NICE model, it's what the planetesimals that drive the NICE model are modeled. You can actually initialize either by setting up the orbital elements or the Cartesian position velocity. You can do either one. It does a conversion for you behind the scenes. So it's very flexible in that way that you can pass just about anything you want. There is a fundamental, like there is a storage system, like by default, everything is stored in the initial conditions file and in Cartesian position velocity. So if you give it some major axis and orbital elements, initial conditions, it does the conversion before it stores it. So again, trying to make life easier by not having to do these things yourself. So okay, so I'm basically what I'm doing is I'm producing a bunch of random particles, test particles, semi-interactive bodies, and just adding them just with this add body method. Add body just allows you to pass in various things. So once I've done that, you should see that I've got a data set that has all these things. So you can open up one of these things and you can see all of the nice bodies I got in here. Sun, Mercury, Venus, Earth. Oh, one aside. The largest body you put into the system automatically gets turned into the central body. So if you want to have a planet-centric simulation, like let's say you want the Earth and Moon as a simulation, and Earth is a central body, you just ask for Earth value, the ID value, and then Moon, Earth becomes the central body. Same thing, Mars. You ask for Mars, Phobos, and Deimos, you'll get Mars as the central body, Phobos, Deimos as the integrated bodies in the system.
If I added the sun in after that,
it will rearrange everything.
it'll rearrange
Yep.
everything.
Yep.
And you were talking yesterday about how it would be nice to have an external perturber.
Yes, I haven't. That's a thing that we need to do. Mathieu's been after me to do it, and I just coding you have to. It's like so many things to do, but yeah, it's something I'd like to do.
Right. So so Swiftest in that sense also wouldn't maybe be set up for like a long-term simulation of like a near passage of another star that could perturb like KBO.
No,
like
you would need a different. That's a rebound is a better choice for something like that.
Okay, that's not my
Yeah.
not my style.
So
anyway.
the kind of runs that I typically, so this is the thing, like rebound's really good for the things Hannah Ryan and his group work on.
Yeah.
They actually haven't put as much into the sort of these like massive body symplectic things like Simba or Mercury as that's why I wanted to do this, like to make a thing to run my style of simulation for like planet formation, satellite formation kind of things.
Yeah.
That's what is really that's where Fraggle comes in. Okay, so again, parameters. What I would say that for those of you on slower computers, just cut down the time step by, actually, I think I'm only doing 1,000 years for this one. So maybe, hopefully that actually runs faster. Let me actually see how fast that ran.
Yeah.
Then I'll start it.
Oh, you give me.
So I did 1,000 outputs and that took about,
It's
Um,
saying 32 threads as its output. Is that likely? Is it actually going to use the 32 threads?
no,
Okay.
it's because you got an older version before I did that switch. It will use it, but it won't be very efficient.
Okay, so I should stop it and define one.
Yeah, there's an environment variable called OMP underscore num underscore threads, just says it equal 1. It should make it go a little faster.
Okay.
Let's see, where's the interval? So the total wall time, it took about 47 seconds on my machine to run that. So if you wanted to cut it down by a factor of 10, just change the t-stop from 1,000 to 100. And then just run it. Hopefully that runs a little bit better and we can actually look at your output.
This is definitely running.
Okay, good.
We're almost halfway through. We're just with your initial.
Okay.
Oh yeah. Oh yeah. 30 threads was taking a lot longer. OMP much faster.
All right. Once you're there, I want to show you just like some more advanced plotting stuff. So it's really where I think it can be really useful. So the X-arrays built-in plot method is really great for like very quickly. I've done this run. I want to see what the sum major axis over time looks like. Boom, one line, do it. It goes. Want to do anything more complicated in it, you really have to go to matplotlib. The X-arrays plot method is based on matplotlib, but it's like a stripped down, very simplified, very sort of like a bare bones version, just to kind of get quick plots out for like data exploration. I just want to be able to quickly see what's going on. When I'm writing my paper, I'm going to want to actually have much more full control over the aesthetics of the plot and the things I want to plot and have all the extra stuff. So, but it's really easy to do that. If you've done any matplotlib, you should be able to, oh, you know what? I accidentally got rid of, I had a whole plotting method for bounding happen here. Was troubleshooting stuff at the last minute.
So it was just the fill between.
Yeah.
That's in the basics. It's in the basics app.
Oh, I love to put that in the basic simulator. Oh, I put it in the wrong place.
It was near the bottom,
Yeah, that's right.
but
Yeah,
yeah.
I was showing an incorrect thing.
It's interesting. Oh yeah, there it is.
Yeah, there we go. Yeah, so basically, oh yeah, this is showing you what doesn't work. Let's get rid of that. So this is showing you how you can set up a matplotlib plot, have your control over stuff, and you just basically pass values to as if it was an NumPy array. Because X-array, because it's based on pandas, it represents the data as NumPy arrays. So actually, if you've used NumPy, there's a habit my students would get into when they were first using this, where they wanted, I guess for comfort reasons, would want to convert everything to NumPy arrays and then do all their data analysis with NumPy. Don't do that. X-array is beautiful. It has all these wonderful things, and it's a superset of NumPy. So you don't have to convert things to NumPy, except in rarely. The few cases where you do. Actually, here's an example where the label, if I didn't convert it to NumPy, that would print something bizarre. See, but almost 9 times out of 10, just leave it as X-array. In fact, X-array is going to be a lot more efficient at doing a lot of things than converting everything into NumPy, and then you lose all the you lose all the names of things, and you lose all that sort of great stuff. If you do decide to use this and use the capabilities of X-array, and there's a learning curve, but you don't have to convert things to lists or NumPy arrays, or just work as long as you can with the X-array, with the sim.data structure, or the X-arrays data set, up until like you run into a wall where you can't, which I would say that most of the time, everything you can do with a NumPy, you can do with the X-array, plus lots of extra stuff.
Interesting.
You lose so much by converting. Okay, so that's a little longer than I had hoped to get through those exercises. I wanted to, if people are interested, I know you're interested, I don't know if you all are interested. I do want to show how you can like compile like a local version of the code and run it, so that if you want to modify things, I also can show you some of the Fraggle examples that we actually have. I don't have notebooks set up because it's not as notebook compatible. But there's a bunch of examples that there's a test run that I run that basically generates all those movies from my plot that's actually in the repository. So I want to say I think technically we have like a half hour left. So what would you all like to see?
I kind of vote Fraggle, but
Yeah.
honestly.
Fraggle? Okay.
Fraggle's good, but what are you interested in?
Uh,
What part are you here today?
I'm just mostly here to be a sponge and absorb because I
Okay.
want to do computational. I want to do this kind of stuff.
All right.
Once I graduate, but
Yeah.
I don't really know all the stuff, so.
Yeah.
Okay. So to proceed, I think we can kill two birds with one stone because there's some examples that show how Fraggle works to make those movies that are in the repository itself. So I think what we can do is we can move to the second phase of the tutorial, which is the sort of development environment part. I like to use Visual Studio Code, so I'm going to leave Jupyter behind and move to VS Code. Does anybody know, do you have VS Code?
Yeah.
Okay, have you used it before? Used VS Code? Okay. So VS Code is typically where I live my life. So I'm going to switch over to my VS Code instance, which is what I was messing with this morning. And let's close this. These are my tab. Okay, so VS Code. What I'm going to do, let's see if I can expand this out chunkier. Oh, you know what? I need to share the VS Code now. I'm just going to share the desktop. Okay. So how do I hide this? Whatever. So I want you to go, I think my instructions were to, okay, I think what we want to do is we want to just get the Swiftest repository. So you did that already before. So what I'm going to go is I'm going to go to building the standalone. Let's see, where's that? Folder. Okay, compiling local. Okay, so you're going to want to clone the Swiftest repository. And the command to do that looks a lot like this. Can you all see that? Let's see if I can move that. Okay.
Should we make a new virtual environment and so on?
No, you don't have to. Just keep them the same, the original, right? Because right now I'm just gonna, we're not gonna compile it yet. We're going to look at the example folder. Okay, so everybody got it? Their Swift is compiled, or is that compiled? Swift is cloned. Okay, so if in VS Code, you should be able to actually see the Swiftest folder that got created. And in that folder is a subfolder called examples. Now, I will caution you that some of these are really out of date. Some of these examples date back to the very earliest days of Swiftest when the API was totally different, and some of these are probably obsolete. So not all of them are going to be useful or working, but one I do know works is the fragmentation example. All right. Now, the fragmentation example is a script that generates movies of all the different collisional outcomes. I use this when when I was first testing Fraggle, and it's become really useful. It makes all the movies I showed off in my talk. In order to run this script, you do need FFmpeg, which is a separate program. So on Homebrew has it, or if you're on Linux, usually you can install it. On my cluster system, all the codes like this are installed through like this module system. So if you want to run the movies, you need to have FFmpeg installed. All right, so the now this script's a little on the complicated side because it's doing a lot. It basically it's automating a set of tasks I built up over the years of like, I want to make a movie of a head-on disruption. Instead of having this one script that does that and I have to modify it by hand, I just wrote one script that basically runs through a menu of different options and generates all these things on the fly. So some of the complexity of the script is just me being fancy with this Python to make it really like automated, which is something I waste a lot of time doing, right? Things like setting up, there's a bunch of parameters that are actually fed to Fraggle to basically control how much output to use and how much, like, what the initial conditions are, how much data output. There's a bunch of like the fiddly little things to do. And things like trying to initialize the vectors of the bodies to guarantee the collision type. So this is a little bit of a trial and error to set these up. So these are, for instance, I'm creating custom bodies that are start with these position vectors and these velocity vectors, which I tweaked until I got the kind of outcomes that I wanted to showcase. Sure. I actually have an item that I want to do is to write a method that creates an impactor that automatically like sets an impactor up with a certain, like, you can ask for a disruption impactor and it just makes it.
I might have code for that already.
Yeah. Well, for Swiftest, where
Yeah.
it's like a method that says, all right, it just automates this stuff.
Yeah.
Rotation vectors, masses, well, G times mass. Okay. And then a lot of the other complexity of this code is to make this kind of extract the data and generate the movies. There's a lot in here that's like me figuring out how to make animations with matplotlib, which is not trivial.
No.
In any way. Matplot, okay, I have a love-hate relationship with matplotlib.
Yeah.
It's so useful. It's designed in such a terrible way. It was designed by my MATLAB people. They wanted to recreate the experience of making plots in MATLAB when they started switching to Python. And so, but the whole philosophy of how MATLAB works is different than Python. And so it's this weird mishmash of like state machine stuff from MATLAB and object-oriented stuff from Python, but functional stuff in Python too. The animation tools are really poorly documented. I actually learned this I created a whole set of tools for a class where I draw like orbits and with arrows and vectors that would automatically and it's very complicated, but I had to dig into the source code of matplotlib to figure out some stuff. Anyway, all that said, once I figured it out, I made the script and Costa makes movies for me. They always look like this because he hasn't touched any of the components. So I always recognize my own script. Anyway, so if you really want me to tell you how it works, I'm happy to do it. Otherwise, this is a nice little template to kind of help set up one of the ways in which you can set up a movie making script using matplotlib. So let's get down to brass tacks here. So really what the script does, most of it is drawing stuff on the screen, but it's going to create these, it's going to create all these cases. See if it just works right off the bat. Okay, so I'm going to go to this.
If I wanted to run this, I would need to get into the other environment.
You should use the same environment you were doing before. It should be compatible.
Okay.
I just have to navigate to the examples. Okay, so, and if I run it.
To run the environment.
All right, so let's see if this is going to work. So I'm just going to create
This is restored. The other one stored.
So go into VS Code and go to your terminal. And just
You actually don't have to be in VS Code, but
wherever you want.
yeah, go in terminal. Let's see. You've got the Swiftest installed here?
Yes, that's installed here.
Okay.
I put the other tab workshop and documents, though it's in two different
So-
places, so maybe.
Well, that's fine. Did you,
somewhere else.
if, is your virtual environment, just activate your virtual environment. That's all you really need to do.
Right.
Okay, now navigate into CD Swiftest examples. Fragmentation movie. Yeah, fragmentation. Yeah, there we go. Okay, and then just write Python and then fragmentation movie.py. Probably loading up. Swiftest for the first time for whatever reason. So let's just do, I'm gonna do like a off-axis supercat. Because that's fun. That is number 4.
Oh, yeah, then I just select a movie to generate.
Yeah,
So-
and it didn't work. Okay, so, oh, because, crap. It's what happened eventually.
It's got a value error.
Yeah. Okay, so this needs some maintenance. I should have tested it this morning, I think. Welcome to my world. Yeah, something changed in the API somewhere. I'm thinking Xarray. This looks like an Xarray. Changed their API in the time since I first made the script into now. So I will have to go fix that. The actual usage of Fraggle is pretty straightforward. And I'm going to go to the documentation page because I think that is basically has the options you would pass. So there are 3 there are 3 collisional models that we've implemented. One's really for testing. Merge, which is just everything's a merger. We call it, that's like the default for the older codes. The bounce, which is actually one of the things that I think Kakubo Onita first tried back a long time ago, which is if you have a collision that would have resulted in disruption, rather than making fragments, you just cause the bodies to bounce off each other. And so you keep them alive, but you don't create new bodies. I implemented that just because I was testing against some older runs and it's an easy thing to implement. So I just put it in there. It's kind of fun. Think about bouncing planets. And then Fraggle, which is my complicated, crazy fragmentation model that does all these things, which I'm hoping to work on shoring up. So by default goes to merge. So if you wanted to use Fraggle, all you have to do is you pass collision model equals Fraggle to the argument list, and that turns on Fraggle. But there's also a bunch of other sort of parameters to choose. The main things that we're still working out what they do is the things that control how big how many fragments you make and what's the smallest thing that you're willing to model in the system. So there are, in a lot of cases, anytime that I want to feed mass to it, the older codes, like people like Hal, they think in terms of G times mass rather than mass, because that's what actually gets computed internally by the code. Anytime you have anything that's got a mass option, I always give the user the option of either passing G times mass or mass, the units of mass. Only one or the other. You can't do them both. So, so in this case, like I could basically, this tells you that the smallest fragment that it will generate. It's like a cutoff, a low value cutoff. It's not going to generate any particles smaller than this amount. There's a sort of empirical reduction factor. There's a sort of number of particles that are based on the size distribution of the impactors, and you have this reduction factor that allows you to sort of scale up or down how many. Again, there's no hard or fast rules of what those are. So it just tells you what the number is, like, for instance, if particular run would generate 300 fragments above min frag, you can set to 30 to only generate 10. All right. So
this is all rather than setting a hard fast.
yes, because it's always going to scale the number of particles to the size of the collision. I wanted to maintain that so that you're not like, I want to make sure that a really big collision makes more particles than a small collision.
So,
Right. There's no way to do it precisely, but I wanted to at least ballpark in that it'll have that kind of behavior. So that's why it's sort of an indirect way of setting some of these things. It takes a lot of trial and error. I'm hoping to make it a little bit more straightforward, but it's just a hard problem in general to get right.
Okay.
And if the code, if I worked, I would have showed it to you, but it doesn't work in that one. So I think it must have something to do with changes either matplotlib or xarray somewhere down the line caused incompatibility. I don't think it's a Swiftest problem. I think it's a matplotlib xarray problem. So did it actually generate the? Oh, do you know what? It actually generated the folder and the initial conditions, and it ran the run. So it actually ran the run. It just let me see if I can actually open up the data, show you. Okay. Let's do this. All right, now we're really limited on the edge. I'm going to try to run a Jupyter Notebook on the fly.
Yep. Now here's where I don't always remember my own API, so I have to go, let's see. I sometimes change the names of things too, which is just bad habit, but it's just, because it's just me. Sometimes it's easy for me just to do stuff, even if it breaks things. Let's see, read, let's see. Yeah. Folder. Okay, so I at least got to read the data in. Too high. Change the name. Oh, RH. All right, I'll have to figure this out. I'm wasting our time now. Okay. You want to see how to compile your own version of the code? Pretty easy. Well, ostensibly easy. Okay, so from the same folder where you've okay, so this is the folder where we've cloned Swiftest into, and I've got my virtual environment already activated. So I've already installed Swiftest. So I'm just gonna uninstall it. Right. So yeah, I want to get rid of it. Most of the time, what should be it? Okay, so there are some prerequisites you need. Homebrew. Okay, let me go through the prerequisites. There's a couple of things you need to kind of have in your system before the guys getting started. So you're building from source. Since we're all Macs, you're going to want to install stuff with Homebrew. Now, with Homebrew, most of what you need is
through here, brew install core utils. That's the core Unix utilities. And you need a Fortran compiler and netcdf Fortran library for the data set. So Homebrew has those. So just use Homebrew to install gfortran and netcdf Fortran. I think probably if you install netcdf Fortran, it probably has to get gfortran too, but I just be on the safe side.
Okay, and if I'm on a,
If you're on like a Red Hat system, it's Yum. If you're on a Ubuntu system, it's apt,
apt-get,
apt-get.
yeah,
The names are a little different. There's actually let's see, in the pipe project at Tomofile actually has some of this stuff laid out for you. Let's see, where's that? The pipe project. I'm not used to seeing my screen so giant.
you can reduce it.
Swiftest. Swiftest. I orient myself to it. Yeah, sorry, I don't remember. There is a way, there's a slightly different, some of these have different names. I think it's like -dev instead of devel with, I think just trial and error, you should be able to find it if it's a Debian based system.
And then is there a way to just try building it before doing the sudo apt-get?
So the command to build, so I always like when I'm doing developing.
Yeah.
I like to build what's called an editable install. When you do pip install, there's a -e thing that you want to use. All it does, it means is when it installs it, it doesn't copy the Python code into your environment folder. It leaves it in place so that if you change any of the Python code, it automatically shows up when you try to run the code. It's more useful for developing. So that's usually the method I use. A pip install. Build isolate. So there's a flag called no build isolation, which basically builds with the tools that you've got installed in your environment. So trying to create a new environment. V just means verbose. Give me some output. E is the editable install. That means don't copy files into the environment repository, the site packages folder. That way I can modify stuff. I don't have two copies of things. Dot just means install whatever's here, and you have to basically look for a Py project at Tomofile or setup.py for the older style, but we use the modern Py project as Tomofile. This file I've got open here is what sort of tells the system how to build and run things. So if I run that, and of course it doesn't work because I have to install. Because there's a bunch of extra. There are a bunch of extra things that need to be installed that don't come along with the. There we go. Okay. Yeah, it's on my documentation page. Right, it tells you that. All right, let's try this again. There we go. Okay. So it's going to compile the Fortran code into a library. There's a little there are hooks that allow it to, through Python, be able to interpret it by Python so that you never see the Fortran. It happens in the background. And because I do this a gazillion times, once I got my packages installed, it works. So that's how you compile it right there. Compile and install it with pip. So now I have my library, because it's editable, the actual library files are stuck here in. Here, there's a standalone command line executable. The actual Fortran code can be run by itself. You don't actually need Python to run it. It's useful for cluster runs, where you can generate your initial conditions in Python, but the actual number crunching is done purely with the executable in Fortran, not with Python. So this is the library that's basically read in by the Python code. Okay. So installed it. All right.
I skipped this stuff, I did this, but when I did this work, then when I did this, I think that I probably needed some of the other.
That error with doing just the pip install in here, once I did, so I did.
Oh.
I did all of that and then tried to do this and it.
Okay, would you put these things in?
Yeah.
I might have to, I adjusted a lot of this stuff last week and it's like.
See me.
That works,
Right, and just try that one, yeah. CMake is not in there.
Or at least not this version. What should I do?
Do pip install CMake.
so we had an error with this line,
Okay, let me see.
Okay, that's working. And then it's angry at me about Python 3.10. So I'll need to get sudo apt apt-get 3.3.
So on my cluster machine, they load those up for us, like, we're not allowed to actually.
This is a
Oh,
private.
it
it's a
is,
private,
yeah. I don't remember how to.
Right.
I think with, actually, there might be, you have to go to the python.org and find like the Linux install script thing. Let's see, what is the process here? What's the not found CMake. Why?
Oh, they only have a 3.15 pre-release.
Okay, this, you had an out-of-date CMake. Oh, no, something else is wrong. Okay, Fortran. Muscle memory, how you
Yeah,
run
let me-
things. Fortran compiler found. Oh. Do you use export or set for setting environment variables? Yeah. Depends on the shell.
Yeah.
So, use left, right arrow, not up arrow. Use the up arrow for. All right, thanks a lot. I'm writing another thing tomorrow for a completely different code, which is less fiddly than this because it uses Rust for the backend instead of Fortran. So this nonsense I'm dealing with right now is not a problem with that code, but the code is a lot less mature.
Yeah, I'll be here for that one too.
Okay.
So, but thank you.
All right,
Sorry,
thanks a lot for
some
coming.
meetings to get to, but this was interesting. Very good.
See. Running. Okay, let's just try this again. Oh, okay. So there's a bunch of other. Give back to your thing. There's another set of things we need to install. Let's see. These are not installed.
Huh.
Yeah, try that again.
That again.
oops, do the install no build isolation.
It looks like I have it.
Weird that it's glitching out because it usually if I just tap up, it like
Hmm.
works, but I don't know what's going on.
Maybe I touched it. Funny.
No,
Sometimes.
we were inside just here and then
Activate your virtual environment.
So I think I downloaded Python 3.13, but then when I tried to make the virtual environment. Maybe this is a separate
cannot
one.
activate the.
Oh, you're not in the right folder. No, you are in the right folder. Your VNV must be on a different folder. I think you're currently in your Swiftest.
So I think I
Yeah.
have to do that, yeah. I'm going to,
Yeah, or you could have put a / VNV,
Right.
but yeah, whatever.
yeah, and then now we wanted to do this stuff.
Let's actually, I'm gonna set your Fortran compiler because that was try that first to see if
Okay.
that does it. If that doesn't, I'll manually set the Fortran compiler again. Okay, so what was the issue now? Not able to, okay. Huh. Fortran code is not able to. That's strange. Okay, so that is puzzling me. It shouldn't be just stopping. This should be running through a whole bunch of
Right.
steps. So.
Different.
It just requires a different Python. Oh, you're on Python. Okay, so somehow you've got it's trying to use an old version of Python. So this satisfy. Somehow it's defaulting to some other, yeah. This is probably some environment variable mess up, I'm guessing. So this is one of the issues. That's why people use Docker. Because your machine probably has some just different collection of stuff installed with environment variables pointing to different things than mine. And so it's causing some mismatch. And I deal with these things by lots of Googling and ChatGPT and so.
Yeah, I can try and do that.
The other thing to do.
Pointing to something else which I had set up.
Yeah,
for different
I'm
colors.
guessing that, yes, this is the problem with Fortran. Like, it's. People still use it, but like. There's a cruft that's built up, like
Yes.
there's like an archaeological, like,
Yeah,
dig to try to understand how it works.
yeah.
When I switched to, my son was actually the one who got me to switch to Rust for other code. And with Rust, because it's like 10 years old, it's built in the era where you could fetch things off the web.
Right,
It just works.
yeah.
It works in Windows. Without even, I didn't have to do anything special. It just worked.
Yeah.
So it's 90% of my time with this code is dealing with this nonsense.
Right.
And I will say that at least on have you used Docker for anything?
Yes, we use Docker to create like the image for our SPH code that we
Okay.
run and put it on the
There is
PC.
all the sort of the GitHub, there's a GitHub system that that builds the packages, that
Okay.
builds the wheels, that
Right,
uses Docker.
right.
And so there are some Docker, I don't have a dedicated Docker. I used to have a dedicated Docker container for this, but it's long obsolete now because I've been using the ones that are up on GitHub actually.
Right,
But it's, there are ways to, there's a tool called CI build wheel that actually can work pretty well and actually can build the wheels for you. It's a little bit more inflexible. It builds like production ready wheels. It
right.
takes a lot of work to get to like a debug system, and if you use Docker, it sort of creates like a Linux environment and does the Docker thing and then comes back, and you have to, there's some ways of like troubleshooting it by going into, actually VS Code has a containers extension that lets you like run a Docker container like it's a machine. And
Interesting.
I've used that before, but I couldn't in 5 minutes tell you how to do it.
No worries.
I think I'm supposed to go have lunch with my, with Kevin.